Hi, thanks for joining me today. We are going to be talking about the sun and where it is in the whole universe and how we know that. So if you have your guided practice ready and ready to do this with me, then let's go ahead and get started. Otherwise, I want you to go ahead and pause, find the section in the lesson that talks about the guided practice, and make sure you do this along with me. It'll help you later. All right, so here it is. Isn't it beautiful? This is our whole galaxy, and we're somewhere in there. Can you believe that? But this picture is not real. How do we know that? Well, how far can you take a selfie away from you? You're going to have an arm out there, right? We have never been this far away from our own galaxy to turn around and take a photo of it. This is an artist's picture. It's a rendering. Now, they used very good technology and lots of science to draw this picture and to make it on a computer. So it's as accurate as they can be, but it is not a real drawing. We have never been this far away. So let's get a better idea of where the heck are we in this galaxy. Welcome to the Milky Way galaxy. If you'd like to go ahead and write that in up here, that's something you're going to need to know if you didn't already. And we are out on one of the arms. We are here. So this is like one of those maps that you've seen where like in a directory of where we are. So obviously this doesn't help us very much, but here's the cool part is that we are halfway down on one of the spirals. Here's the cool part. On your notes, it says, every star you see in the night sky is in this yellow circle right here. Every star that we can see. All the rest of them, they're too far out for the naked eye to see. You're going to need something else, like a telescope. But you can see our sun is just one of many, 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 many stars. And I always ask students that, like, what's the closest star to us? And some people actually know that there's a star called Proxima Centauri, and it's our next closest star. But our closest star is the sun. That's the one. But it looks so much different, doesn't it? Than when you look at all those other stars. Take a look. Oh, my bad. This is the real view of the Milky Way. This is one side, and you can actually see little lines around it. This isn't in your notes, but I just wanted to show you a real photo. This is like if you were able to take a picture of just your toes or just the top of your head. This is the other side of the Milky Way that we can see from our location, and it looks really cool. It looks like a little bit of spilled milk in the sky, hence the name. So I just wanted to show you a real photograph of it. Anywho, so when we think of the night sky, we think of this picture right here, okay? And I've got the Little Dipper photographed for you. Now, they drew in the line so you could see it actually does look like a little pot or a little spatula, not spatula, a ladle that like could be dipped in water. That's where the name comes from. But our sun looks so much different. I mean, all those, they just look like what? Little cutouts in black cloth. They're all like little dots, right? That's what a star looks like. No, stars look like this when you get closer. So our sun, as you know, is a big, giant, glowing ball of burning gas, hydrogen and helium. It's crazy hot. It's crazy big. And it's 93 million miles away. That's really far. That's really far. However, if you were to think about it in terms of light, the sun is only 8 light minutes away. That means that the light that leaves the sun is only going to take 8 minutes to reach our eyes. Now, when you look up at the Little Dipper, every single one of those stars, there's 7 major ones, are all different distances away. The closest one is 97 light years away. And just to remind you that a light year is a measure of distance, and that distance is almost 10 trillion miles for each light year. So how many miles is that? It's really hard to say. It's 5.3 quadrillion miles away. Just to give you an idea, that's the number 5.3 with 14 zeros on it, miles away. Okay, so if you were to get closer to one of those stars, they would start to look more like the picture we have on the right. But our sun, even though it's 93 million miles away, it's so much closer. But every single one of those stars has its own color, its own temperature, and its own size, and they're all burning balls of gas. Okay, so just a reminder, if you watched our HR diagram video, our sun is middle everything. It is middle temperature. There are stars that are less hot, and there are stars that are more hot. It is middle brightness. There are stars that are dimmer. There are stars that are brighter. It is middle color. It is not the least hot color of fire, and it is not the most hot color of fire. It is considered a yellow star. Now, sometimes this can look a little red or a little orange, just depending on how the sun's light waves are coming in through our atmosphere, but it really is considered a yellow sun. It is also middle-aged. It is like a college student, if you were to talk about it into terms of a life cycle. So everything about our sun is middle. Middle brightness, middle temperature, middle color, middle-aged. Middle of the middle of the middle. That makes it easy to remember. Okay, so how do they know all this? How do they know that those temperatures, and how do they know those colors and those sizes? I can only look up and see so much, and that's because we're not getting the full picture when we only use our eyes. Turns out there's all these other kinds of waves that we can use besides just visible light. Now they call this the electromagnetic spectrum. Okay, the electromagnetic spectrum shows you all the different kinds of waves in one spot. So you can see they're organized so that we can see them all at one time. But this isn't how they travel. Gamma rays go their way, microwaves go their way. They're all a little different. Okay, so looking at the top of this picture, you can see that these are organized by wavelength. Now, sometimes this is switched. Sometimes they put radio on this side and gamma ray on this side. Either way, it's all organized the same. So we're going to start over here on the radio side. You've heard of radio waves, and that's, of course, the sound that comes through your radio. Gets you some music, gets you a call on the phone, but also it lets them, when the scientists point it outward, out into space, they can learn a lot about how galaxies and planets are actually, what they're composed of, what they're made of. And they use an actual radio telescope for that. Okay, and these waves are very, very big. Now they pass through us completely harmless. They pass through buildings, they pass through walls, they pass through windows, they pass through people. Okay, and they're completely harmless. But some of them are as tall as a building. Now here's the cool part. All of these different kinds of waves, they travel at the exact same speed, which is really, really, really fast. It's 300,000 kilometers per second. So 1/1000, boom, 300,000 kilometers that away. 2 seconds, boom, boom, 600,000 kilometers that away. But they take different step sizes to get there, okay? So radio is going to take these big, giant steps. It's not going to take many in 1 second, but no matter what, it's going to be 300,000 kilometers away at the end of that 1 second. Now, moving in a little bit, we can see that we've got another kind of wave here. Microwaves, just like your microwave oven, that's right. They are a little bit closer together, and they can be not as big. They might be around an inch or maybe the size of your foot. And we use these waves. Scientists have found ways to use these waves on Earth. We pop popcorn, we heat up food, but then they can also use them by sending them back out into space. And they're not stopped by weather, whereas radio waves, they had a little trouble getting through the weather. And they can find out all kinds of stuff about the structure of galaxies by using microwaves. They send these out, they hit something, they bounce back into a microwave telescope, and we can learn a lot about it. They also use microwaves when using radar and sonar and satellites. Now, of course, radar has more to do with radio, hence the name, but there's some different kinds that can come at that. Moving down the cycle, we're going to get, down the spectrum that is, we're going to get into infrared. You've heard of infrared, and you might not have seen it. You know, so far, none of these waves have been where you can see them. But infrared are the first ones you can feel, because infrared is heat. So we feel these, the waves coming from the sun, a fire, that annoying metal slide that they always have on the playground. What's up with that? But they use these, they can use infrared waves to actually see dust. Dust is very hard to see, but it's everywhere out in space, and they can actually use that to study it. We can also use infrared to study our cloud structures, our ocean temperatures, and of course our climate change, which is a big deal. Now, none of those have been visible to the eye, but they have given us so much information. Right smack dab in the middle are the only wavelengths that we can actually see, and they're the visible ones. This is all the colors. Everything from the deep, deep purples and violets all the way up to the reds. Hence the name infrared that's right after it. Okay, so this is all that our eyes can see. Other animals, they can see some infrared, or sometimes they can see some ultraviolet, but our eyes can only see these kind of wavelengths, and they just line up perfectly for the receptors that are in our eye, like the little rods and cones, and really fascinating stuff, but I'll get off topic if I get talking about it. Okay, so after that, the wavelengths get even tighter. Ultraviolet. Ultraviolet can actually start to be the first ones that can harm us. If you stay out in ultraviolet waves too long, you can get a sunburn. This is the type of light waves that the sun also puts out that can hurt us. You can get a sunburn. You can actually hurt your eye. That's why we don't look at solar eclipses too long, because the ultraviolet can hurt us. Okay, it can also sanitize things, so that's handy. After that, we get X-rays. These are getting very small. These waves are getting very tiny, and they can actually pass through us, but they can't pass through solid bone. And so that's why it's good to use them for when you break a bone or when you need to look at your teeth. They can also place X-ray detectors on satellites, and they can study all kinds of objects in space and teach us a lot about what's out there. And finally, the last ones that sound like they should be out of a comic book area are gamma rays, which are not going to help us with radioactive spiders, actually. They are going to be the shortest wavelength that we have. Now remember, just like the radio waves, they're still going to travel 300,000 kilometers per second, but they're going to take itty bitty steps in order to get there in 1 second. And so they also can be used to have help people kill cancerous cells, but they also can help us learn how the whole universe began. This is what helped us prove the Big Bang Theory. So very, very interesting stuff there. And we will study that as well. Okay, so moving on to our next one, and I hope you wrote those in as we went. Otherwise, you can pause here and write those in. But finally, if we could see other kinds of waves, our night sky would be like constant fireworks. There are constant gamma ray bursts that just come off of stars. And so we would see them all the time, just pew, 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 pew. It would be beautiful. But we can't see them. Our eyes don't capture that kind of wavelength of light. So this is what we see. And there's a little UV in there that we also can't see. But again, some animals can. Okay, and it's not on your notes, but just to remind you, the good news is we don't normally have to memorize these. When they show up on tests, they would just kind of point at like this area and say, hey, if something had a frequency of 10 to the 19th, what kind of wavelength would they be studying? And you would just look right up and go, oh, that's X-ray. So that's all we really have to know, is that every single one of these waves can help us. Thanks for watching, and have a great day.